Out in the cosmos, beyond the comfort of our tiny blue planet, exist forces so extreme they defy comprehension. Black holes that can shred stars like paper. Invisible particles that might be able to move faster than light itself. Theoretical objects so bizarre that if their existence was proven, it would break the laws of physics as we know them. Space is not just a vast and empty void, it's a playground of unimaginable power. Some of these cosmic phenomena are real, some are still theoretical, and others might only exist in the deepest equations of physics. But they all remind us that the universe is far stranger than what we can imagine. Planck scale mysteries, where space, time, and terror converge. There lies a realm of extreme uncertainty when the universe is shrunk down to the smallest possible scales. This is the Planck scale, at distances smaller than 1.6 multiplied by 10, to the power of negative 35 meters, and time shorter than 5.4 multiplied by 10, to the power of negative 35 negative 44 seconds. The rules of physics, as we know them, break apart, leaving behind a landscape of wild, unpredictable behaviour. If we could peer into this hidden layer of reality, we would see something unlike anything in the familiar world. We think of space as a smooth and continuous stage where objects move and events unfold. But at the Planck scale, this illusion falls apart. Space may not be a background at all, but rather a chaotic, ever-changing structure. Some theories suggest that it is foamy and turbulent, filled with microscopic fluctuations. Tiny regions of space might constantly appear and disappear, creating a churning, dynamic fabric. These fluctuations are not just small distortions, but could be fundamental shifts in the nature of reality itself. Time, too, may become meaningless at this scale. In our normal experience, time moves forward in a steady, predictable way. But in the deep structure of the universe, it might be broken into indivisible units, much like frames in a film. Instead of flowing smoothly, time could jump from one instant to another, making the idea of past, present, and future blur into something unrecognizable. Some physicists even suggest that time might not exist at this level at all, but rather emerge from a deeper, unknown structure. The consequences of this strange reality are profound. One of the biggest questions is whether space and time are truly fundamental or whether they are just approximations of something deeper. If they are not fundamental, then what lies beneath them? Some ideas suggest that the universe could be built from pure mathematical relationships, with space and time emerging as useful descriptions rather than absolute truths. Others propose that space and time might be woven together from networks of tiny quantum connections, much like a web forming a larger pattern. The violent and unpredictable nature of the Planck scale raises another unsettling idea: the possibility of quantum chaos. Unlike the stable and predictable world of classical physics, the quantum realm is filled with uncertainty. Particles can exist in multiple states at once, and their behaviour is determined by probability rather than fixed rules. At the Planck scale, this chaos reaches a level that is difficult to comprehend. Space itself might fluctuate so wildly that it becomes impossible to define any fixed position or distance. This means that if we could somehow shrink down to this scale, we would not find a simple, orderly grid, but rather a swirling, chaotic mess where nothing can be pinned down. One of the strangest possibilities is that miniature black holes could constantly form and vanish within this quantum foam. In normal conditions, black holes are massive objects formed when stars collapse under their own gravity. But at the Planck scale, energy could be so concentrated that tiny black holes might appear for the briefest moments before disappearing again. These fleeting objects could warp space and time in unpredictable ways, further adding to the sense of disorder. If true, then the very foundation of reality might be shaped by an endless dance of tiny gravitational distortions. The idea that space and time themselves are unstable suggests that everything we know, our world, our bodies, even our thoughts, rests on a foundation that is not solid at all, but rather in constant motion. The ground beneath us may not be truly fixed, but instead part of a deeper structure we do not yet understand. This mystery has real consequences for our understanding of black holes, the Big Bang, and the overall nature of the cosmos. If space and time are fluctuating wildly at the smaller scales, then the idea of a singularity, a point of infinite density, may not make sense at all. Instead of being a single, infinitely small point, the centre of a black hole might be a place where quantum effects reshape the rules of physics, preventing an actual singularity from forming. The same could be true for the beginning of the universe. Rather than a single, explosive event, the Big Bang might have been a transition from one quantum state to another, avoiding the paradox of an infinite starting point. The Planck scale also challenges our ability to measure reality itself. In everyday physics, measurement is straightforward. Objects have definite positions, speeds, and sizes. But in the quantum world, measurement affects the thing being observed. At the Planck scale, this effect becomes extreme. If we try to measure space at this level, the very act of measurement might cause violent fluctuations, making it impossible to get a clear result. This means that reality at this scale is not just hidden from us, it may be fundamentally unknowable. Some theories suggest that even the laws of physics might change at these extreme scales. Constants that seem fixed, such as the speed of light or the strength of gravity, could shift. If this is true, then the universe we experience might be just one possible version among many, shaped by the specific way these deeper forces interact. While current technology does not allow us to directly explore the Planck scale, scientists are searching for clues. Some hope that future particle accelerators could create conditions extreme enough to reveal traces of quantum gravity. Others look to the cosmos, searching for subtle patterns in the afterglow of the Big Bang that might hint at the chaotic fabric of the universe's foundation. Black holes, too, might hold answers, as their intense gravity could amplify quantum effects in ways that reveal new insights. The Planck scale represents the ultimate frontier. If we can unravel its secrets, we may not only understand gravity at its most extreme, but also uncover a deeper reality hiding beneath everything we know. Quantum black holes, microcosms of chaos. Black holes are often imagined as massive, devouring objects that lurk in the depths of space, swallowing stars and distorting time. They are the heavyweights of the universe, formed when enormous stars collapse under their own gravity. But there is another possibility, one far stranger. If the universe follows the rules of quantum mechanics even in the realm of gravity, then black holes might not be limited to the colossal. They could exist in miniature form, emerging from the chaotic fluctuations of the quantum world. These tiny black holes, sometimes called quantum black holes or micro black holes, challenge what we know about space and time. In the world of classical physics, a black hole forms when an object becomes so dense that its gravitational pull overcomes all other forces, preventing anything from escaping, not even light. The boundary surrounding this region is called the event horizon, a point beyond which nothing can return. But this picture is based on general relativity, which works well at large scales, but breaks down in the quantum realm. If gravity has a quantum side, then black holes could form in ways we never expected, possibly appearing in the smallest corners of reality. In the churning foam of space itself, microscopic regions might temporarily collapse under their own gravity, creating tiny event horizons that vanish almost as quickly as they appear. These black holes wouldn't be formed by collapsing stars, but rather by the fundamental nature of quantum space. Unlike their massive cousins, they wouldn't last long, evaporating through a process known as Hawking radiation. Hawking radiation, proposed by physicist Stephen Hawking, suggests that black holes are not entirely black. Due to quantum effects near the event horizon, particle-antiparticle pairs can spontaneously form. Sometimes one of these particles falls into the black hole, while the other escapes, carrying away a tiny amount of the black hole's mass. Over time, this slow leakage would cause the black hole to shrink and eventually disappear. For large black holes, this process takes an incredible amount of time, longer than the current age of the universe. But for tiny black holes, the process happens much faster. If a micro black hole formed, it might evaporate in an instant, releasing a burst of high-energy particles. Some scientists believe these quantum black holes might have formed in the early universe, when the cosmos was incredibly hot and dense. During this time, space itself was filled with intense energy fluctuations, possibly creating tiny black holes that live briefly before vanishing. While they may no longer exist today, they could have influenced the structure of the cosmos in those early days. The Large Hadron Collider, or LHC, the most powerful particle accelerator on Earth, was once thought to have a small chance of producing such objects. If that were true, it would provide direct evidence that gravity behaves differently at extremely small scales. However, no such black holes have been observed, leaving the question open. The idea of quantum black holes also connects to one of the greatest mysteries in physics, the fate of information. In classical physics, information about an object is never truly lost. Even if something is burned, crushed, or transformed, the underlying information about its state still exists in some form. But black holes seem to break this rule. If something falls into a black hole, does its information vanish forever? This is known as the black hole information paradox, and it remains one of the biggest unresolved questions in physics. For massive black holes, this paradox is difficult to test, but for quantum black holes, the stakes are different. If these tiny black holes form and evaporate quickly, then the question becomes even more pressing. Where does the information go? Some physicists believe that quantum mechanics must hold the answer, possibly through subtle connections between space, time, and entangled particles. Others suggest that information might be encoded on the event horizon itself, much like a hologram. Some theories propose that quantum black holes might not evaporate entirely, but instead leave behind a remnant, a stable, ultra-small object that no longer emits radiation. These remnants could act as hidden storage for lost information, carrying secrets about the fundamental structure of space. If they exist, they could be scattered throughout the universe, waiting to be discovered. The existence of quantum black holes would provide a direct link between quantum mechanics and gravity. They might also explain cosmic mysteries, such as the nature of dark matter. Some researchers have speculated that tiny black holes, left over from the early universe, could be a component of the invisible matter that holds galaxies together. If this idea is correct, then quantum black holes could be currently shaping the cosmos. Tachyons and the illusion of speed, revisiting faster-than-light phenomena. Tachyons were first introduced in the 1960s as a mathematical possibility rather than a confirmed reality. In special relativity, the speed of light acts as a universal limit. No known particle with mass can ever reach or exceed this boundary. However, when physicists explored equations from a different angle, they found that certain solutions allowed for particles that never travelled below the speed of light. These hypothetical particles, called tachyons, would not simply break the light speed barrier, they would exist in a state where moving slower than light was impossible. The properties of tachyons are unlike anything found in nature. For one, their speed increases as they lose energy, which is the opposite of how normal particles behave. In contrast, when a tachyon gains energy, it slows down but never drops below the speed of light. This inverse relationship between energy and velocity is one of the strangest aspects of tachyons, and a major reason why they remain in the realm of speculation rather than observation. If tachyons were real, their behavior would make them nearly impossible to detect with traditional scientific methods. If these particles could travel faster than light, they would also be capable of violating causality, the principle that causes must always precede effects. This would mean that information could travel backward in time, creating paradoxes where an effect could, in theory, occur before its cause. A message could be sent into the past, or an event could influence something that happened before it, completely disrupting our understanding of how time unfolds. This is one of the biggest reasons why many physicists are skeptical of tachyons being more than just a mathematical curiosity. Despite the theoretical problems they pose, tachyons appear in some versions of quantum field theory and string theory. In these models, tachyons are not necessarily real particles, but indicators of instability. When certain equations predict tachyons, it often suggests that the theory itself needs to be adjusted. Instead of proving that faster-than-light particles exist, their appearance can mean that the current understanding of physics is incomplete, or that a deeper layer of reality has yet to be uncovered. Some scientists have proposed that if tachyons exist, they might be confined to hidden dimensions or alternate layers of reality beyond our perception. In this view, tachyons might influence the universe in ways we do not yet understand, but their effects would be subtle or indirect. They could play a role in shaping space-time on a quantum level, interacting with other particles in ways that do not violate causality in an obvious way. If this is the case, it could mean that faster-than-light motion is not as impossible as once thought, but rather that it operates under rules we have yet to discover. Experiments designed to detect tachyons have so far come up empty. Scientists have searched for signs of these elusive particles in high-energy physics experiments, cosmic rays, and even in the behaviour of light passing through certain materials. While some past experiments have hinted at unexplained effects that resemble tachyon-like behaviour, none have provided definitive proof. The challenges of detecting something that fundamentally defies normal physics make this search one of the most difficult in modern science. One of the most tantalizing connections between tachyons and real-world physics comes from quantum entanglement. In experiments with entangled particles, information appears to be shared instantaneously between distant points. Some have speculated that this could be evidence of tachyon-like influences operating at a hidden level, allowing information to move faster than light without violating relativity in an observable way. While no direct link between entanglement and tachyons has been proven, the similarities between these two phenomena continue to intrigue researchers. If tachyons do exist, they could open the door to entirely new forms of communication and technology. A civilization capable of harnessing tachyons might be able to send messages across the universe instantly, bypassing all limitations. This idea has even influenced science fiction, where tachyon-based communication is often depicted as a way to break free from the constraints of relativity. However, without experimental evidence, such ideas remain purely speculative. Inside the abyss, theoretical explorations of black hole interiors. For a long time, scientists could only speculate about what might exist beyond a black hole's singularity. The idea of infinity in physics is troubling. It suggests that something is missing in our understanding, that an even deeper theory is needed to describe what truly happens inside. If the singularity is real, it represents the ultimate destruction of anything that crosses the horizon. Every particle, every atom, every planet swallowed by the black hole would be torn apart by immense gravitational forces, eventually meeting its end at the central point of infinite compression. But some scientists believe the singularity may not exist in the way we imagine. One idea is that the core of a black hole is not a singularity at all, but a chaotic, roiling mass of quantum interactions. If space itself becomes unstable under such extreme conditions, then the heart of the black hole might be a tangled web of fluctuating energy rather than a simple, crushing point. Some theories propose that the intense gravitational forces cause space to fold in on itself, creating complex, unpredictable structures. Other theories suggest that the singularity might be avoided altogether through an unexpected twist in space-time. Some propose that black holes could lead to other regions of the universe, or even to entirely different universes. This idea, inspired by solutions to Einstein's equations, suggests that instead of being a dead end, the centre of a black hole might act as a bridge, a wormhole connecting distant points in space. Some have proposed that space and time may not continue smoothly inside the event horizon, but instead reach an abrupt end. If true, then falling into a black hole would not mean being crushed at the centre, but rather experiencing the total breakdown of space-time itself. Some researchers have tried to develop alternative models of black hole interiors that do not involve singularities at all. One such idea is the concept of a fuzzball, proposed in string theory. According to this idea, black holes are not empty voids with singularities at the centre, but instead are made up of incredibly dense strings of energy, woven together in a way that eliminates the need for a singularity. Another proposal is that black hole interiors might contain a form of exotic matter that prevents total collapse. Some versions of this idea suggest that when matter falls in, it does not get crushed to a singularity, but instead is transformed into an ultra-dense state, possibly forming something like a black star rather than a true black hole. If this is the case, then black holes might not be completely inescapable, but instead could slowly leak their contents over time. In normal physics, information about an object, its shape, structure and properties, is never truly lost, even if it is changed or broken apart. But in a black hole, everything that crosses the event horizon appears to vanish forever. Some researchers believe that the answer to this paradox lies in the quantum structure of space itself. One idea is that information is somehow stored on the event horizon in a scrambled but still recoverable form. This would mean that black holes do not truly erase information, but instead encode it in a way we do not yet understand. Others suggest that black holes might eventually return their information to the universe through subtle quantum effects, possibly through the process of Hawking radiation. If this is true, then black holes are not ultimate destroyers, but instead act as strange, hidden vaults of cosmic information. There is also the possibility that black holes are not permanent. While massive black holes in the centres of galaxies may last for billions of years, smaller ones might slowly evaporate, releasing their contents in a final burst of radiation. If this happens, then the mystery of their interiors might not last forever. Eventually, they could reveal their secrets as they disappear. Topology of the cosmos. Unconventional geometries in a warped universe. The shape of the universe is a profound mystery. On the larger scales, beyond galaxies and clusters, space itself may follow an unexpected geometry. While we often picture space as an endless, featureless expanse, the universe could be far more intricate, shaped by deeper principles of topology. Scientists describe the universe's overall shape in terms of curvature and topology. Curvature refers to whether space is flat, positively curved like a sphere, or negatively curved like a saddle. Current observations from the cosmic microwave background, or CMB, suggest that the universe is nearly flat. However, flatness does not necessarily mean infinite. Just as the surface of a cylinder is locally flat, but still loops back on itself, space could be connected in unexpected ways. A finite universe could still have no boundaries if its topology allows for paths that loop back on themselves. In such a universe, travelling far enough in one direction might bring you back to your starting point, much like walking around the surface of a planet. This could mean that the galaxies we observe in different parts of the sky might actually be duplicate images of the same galaxy, seen at different points in time, due to the way light has wrapped around the cosmic structure. One of the simplest topological models is the toroidal universe, shaped like a higher dimensional version of a donut. In this scenario, space is connected in such a way that movement in one direction eventually loops back, but without the curved surface we associate with a normal donut shape. If the universe has a multi-connected topology like this, astronomers searching for distant galaxies might actually be seeing repeated versions of the same structures from different perspectives. More exotic possibilities exist as well. The universe could have a shape resembling a Mobius strip, in which space twists upon itself so that travelling along one path could flip your orientation. This would mean that an object travelling through space could return to its starting position mirrored. Such a structure would challenge our understanding of symmetry on cosmic scales, yet remains a mathematically viable possibility. If space is finite, but connected in complex ways, it could also affect the CMB. Scientists have searched for patterns in this radiation that might indicate repeating structures, looking for matching temperature fluctuations on opposite sides of the sky. So far, no definitive evidence has emerged, but the search continues, as even subtle hints of a multi-connected universe could reshape our understanding of cosmic history. Another way topology might influence the universe is through its expansion. The standard cosmological model assumes that space expands uniformly in all directions. However, certain topological features could introduce anisotropies, meaning that expansion might be slightly different along different axes. If the universe had a shape resembling a squash sphere or an elongated torus, expansion rates might vary in different directions, leaving imprints on the distribution of galaxies. If the universe is truly infinite, then any structure, no matter how vast, will always be part of a still larger system. But if the universe has a finite, yet connected shape, it means that the cosmos is not boundless, but instead follows a hidden pattern. This would mean that the fundamental nature of space itself is more like a carefully arranged puzzle than an open-ended expanse. Some researchers suggest that the large-scale distribution of matter might already hint at unusual topology. Galaxy surveys have mapped enormous structures, revealing patterns that might be explained by underlying geometric connections. If certain configurations repeat at vast distances, it could indicate that space folds back on itself. While these signals remain speculative, they inspire new ways of thinking about cosmic architecture. The relationship between topology and dark energy is another open question. Dark energy drives the accelerating expansion of the universe, but if space has an unconventional shape, it could interact with this expansion in unexpected ways. Some theories propose that certain topological configurations might even explain dark energy's mysterious effects, suggesting that what we interpret as an unseen force might be a consequence of hidden spatial properties. Temporal dissonance, the curious time distortions near black holes. The stronger the gravitational field, the more space and time are stretched. In everyday life, this effect is too small to notice, but near an ultra-dense object like a black hole, it becomes extreme. The closer an object gets to the event horizon, the greater the distortion. To a distant observer watching from safety, an astronaut approaching a black hole would appear to slow down, their movements becoming more and more sluggish until they seem frozen just before crossing the horizon. But from the astronaut's perspective, time would feel normal. The universe outside, however, would appear to speed up as distant stars and galaxies aged in fast forward. This strange warping of time means that black holes can act as one-way time machines. Someone who orbits near the event horizon for a while before escaping would return to find that far more time has passed in the outside universe. The closer they get to the black hole, the stronger this effect becomes. If a person could survive near the edge of an ultramassive black hole for a few hours, entire centuries could pass for those farther away. This isn't theoretical. Scientists have confirmed that gravity slows time even on Earth. Satellites orbiting our planet experience time just a tiny fraction of a second faster than we do on the surface. It is only near a black hole that this effect becomes strong enough to alter reality in dramatic ways. But something even stranger happens when someone actually crosses the event horizon. From the perspective of an outside observer, they never quite fall in. Instead, they appear to slow down infinitely, never quite reaching the point of no return. This is because light itself is stretched into longer wavelengths, eventually fading into invisibility. The person falling in, however, would notice nothing unusual as they pass the horizon. Time would continue normally for them, and their journey toward the center of the black hole would proceed as expected. The reason for this contradiction is that time is not a universal constant. It is relative, changing depending on where and how you observe it. For someone unlucky enough to be caught in the gravitational pull of a black hole, the flow of time would become increasingly unpredictable. If the black hole is small, tidal forces would rip them apart long before they could reach the event horizon. But if the black hole is ultramassive, the experience would be different. The event horizon would be so large that a person might not even realize when they had crossed it. However, the journey inward would be inescapable, leading toward whatever strange reality exists at the core. There is another strange possibility. Some theories suggest that black holes might not simply trap time, but could, in certain circumstances, lead to other parts of the universe, or even different timelines. If wormholes exist within black holes, it could mean that falling into one might not lead to destruction, but instead to an entirely different region of space or time. However, no evidence has confirmed this, and most calculations suggest that any such passage would be highly unstable. Another mystery comes from what happens as black holes evaporate. If they eventually disappear completely, what happens to the time distortion they created? Did time itself stretch and slow permanently within the black hole, or does it snap back into place when the black hole vanishes? Some theories suggest that black holes store information about the time and matter they consume in ways we don't yet understand. Others suggest that time distortions may be irreversible, leading to deeper paradoxes about the nature of reality. Scientists are still working to understand these questions. The universe, it seems, does not have a single universal clock. Instead, time itself is woven into the shape of space, bending and twisting under the pull of gravity. White holes, cosmic inversions, and the limits of causality. Unlike black holes, which consume everything that comes too close, white holes are thought to do the exact opposite. They expel matter and energy, allowing nothing to enter. If black holes are one-way doors into the unknown, white holes would be the other side, regions of space where matter is forcefully ejected rather than drawn in. No confirmed white hole has ever been observed, but their existence is mathematically possible within the same equations that describe black holes. They stand as a strange, unexplored frontier in our understanding of gravity and time. The idea of a white hole comes from the equations of general relativity. When solving these equations for black holes, there is a way to flip the solution, reversing the flow of time. This theoretical object would behave like a black hole running backward. Instead of pulling in light and matter, it would push them away. Instead of trapping anything that crosses a boundary, it would prevent anything from getting close. A spacecraft approaching a black hole would never be able to escape, but one approaching a white hole would never be able to get inside. A black hole forms when a massive star collapses. But what could cause a white hole to form? If a black hole is a bottomless pit, then a white hole should be a fountain, endlessly spewing matter. But where does that matter come from? Some theories suggest that white holes might be linked to black holes through wormholes, forming a bridge between different parts of space, or even different universes. Matter falling into a black hole in one place might reappear from a white hole somewhere else, though such an idea raises more questions than answers. Some scientists have proposed that the Big Bang itself might have been a kind of white hole. If white holes can appear spontaneously, rather than forming from collapsing stars. The sudden expansion of space and matter at the birth of the universe could be explained as a white hole eruption. Unlike black holes, whose event horizons prevent information from escaping, a white hole's event horizon would act as a barrier preventing anything from entering. In this view, our entire universe might be the interior of a vast white hole that burst into existence in a higher dimensional space. Some researchers have even suggested that the mysterious high-energy bursts detected in deep space, such as gamma-ray bursts, could be the signatures of white holes expelling matter. These bursts are among the most powerful explosions known, capable of releasing more energy in seconds than the Sun will emit in its entire lifetime. While most gamma-ray bursts are thought to come from collapsing stars or merging neutron stars, some scientists wonder if a fraction of them could be caused by white holes briefly flickering into existence before vanishing. One of the biggest mysteries in physics is what happens to information that falls into a black hole. Some theories propose that information swallowed by a black hole could eventually be released by a white hole, preserving the balance of cause and effect. This could mean that white holes are not just theoretical oddities, but essential parts of the universe's accounting system, ensuring that no information is ever permanently destroyed. Despite these intriguing possibilities, there are significant problems with the idea of white holes. Unlike black holes, which form naturally through well-understood processes, white holes have no clear way of coming into existence. The math allows them to exist, but nature does not seem to produce them in any obvious way. Even if one did form, it would likely be unstable, collapsing almost instantly under its own gravity. Most physicists believe that if white holes ever existed, they would have disappeared long ago. Strange matter realms, the exotic cause of neutron stars. Neutron stars are among the most extreme objects in the universe. Born from the explosive deaths of massive stars, they contain more mass than the Sun, but are packed into a sphere no larger than a city. Their gravity is so intense that atoms collapse, leaving behind a solid core of neutrons pressed together in a way never seen on Earth. The outer layers of these stars are well understood, composed of tightly packed neutrons with a crust of atomic nuclei. But the deeper one goes into a neutron star, the stranger the physics becomes. Some scientists believe that at the very heart of these stellar remnants, the rules of matter could change entirely. This is where a mysterious form of matter might exist: strange matter. Normal matter, the kind that makes up everything from planets to people, is built from atoms. Each atom contains a nucleus made of protons and neutrons, and those particles, in turn, are made of even smaller components called quarks. On Earth, quarks come in only two stable types, up quarks and down quarks. But in the extreme pressures of a neutron star's core, something different might happen. The density might be so high that neutrons themselves break apart into their constituent quarks, forming what is known as a quark-gluon plasma. Among the quarks that appear in this environment are strange quarks, which normally do not exist freely in nature. If enough strange quarks accumulate in one place, they could form a stable new type of matter, strange matter. Strange matter would be denser than normal nuclear matter, and some theories suggest it could be the most stable form of matter in the universe. If this is true, then the cores of neutron stars might not be made of neutrons at all, but instead of this exotic, self-sustaining substance. The existence of strange matter would imply that these neutron stars are not just dense stellar remnants, but something far more unusual: strange stars. A strange star would be fundamentally different from a regular neutron star. Its surface would likely be smoother, lacking the crust of atomic nuclei that coats neutron stars. Its density would be even greater, pushing the boundaries of what we understand about matter. Some theories suggest that strange stars could produce incredibly powerful magnetic fields, even stronger than those observed around magnetars, the most magnetized neutron stars known. If strange matter is stable enough, it could even mean that neutron stars gradually transform into strange stars over time, as their interiors are converted into this new form of matter. One of the more unsettling possibilities is that strange matter might be contagious. If a piece of strange matter were to come into contact with normal matter under the right conditions, it could theoretically convert it into more strange matter, leading to a runaway reaction. This has led to speculation that if strange matter were ever created on Earth, it could begin transforming everything it touched, eventually turning the entire planet into a strange star. However, most scientists believe this is unlikely, as the conditions required to stabilize strange matter likely only exist inside neutron stars. There are some observational clues that suggest strange matter might be real. One of them comes from the study of neutron star collisions. When two neutron stars merge, they produce gravitational waves. These collisions also release enormous amounts of energy, momentarily exposing the innermost layers of the stars. Some researchers believe that the behaviour of these collisions hints at the presence of strange matter. If strange matter is more stable than normal neutron star matter, then after a collision, instead of forming a black hole immediately, the merged object could briefly exist as a massive strange star before collapsing. The precise details of these events are still being studied, but gravitational wave observations continue to provide valuable clues. Another possible sign of strange matter comes from fast radio bursts, brief but powerful flashes of radio waves detected from deep space. Some scientists suspect that these signals might be linked to neutron stars suddenly undergoing a phase transition, where their cores transform into strange matter. If true, this would mean that fast radio bursts are not just random cosmic events, but signs of neutron stars evolving into strange stars, releasing massive amounts of energy as their internal structures shift. Despite the intrigue surrounding strange matter, there is still no direct evidence that it exists. All of our current knowledge about neutron stars comes from indirect observations, such as measuring their masses, sizes, and the signals they emit. The conditions inside neutron star cores are impossible to replicate on Earth, making it difficult to test these ideas in a laboratory. However, upcoming space telescopes and more advanced gravitational wave detectors might provide new insights. Some scientists hope that precise measurements of neutron star properties will reveal whether their cores contain normal nuclear matter, quark matter, or something even stranger. If strange matter is real, it would suggest that neutron stars are not just simple stellar corpses, but laboratories of extreme physics, where new forms of matter emerge. It could also raise the possibility that strange matter exists elsewhere in the cosmos, perhaps in small, stable lumps drifting through space. Whether or not it exists, the continued study of neutron stars improves our understanding of matter under extreme conditions. These dense remnants of ancient supernovae may hold the key to unlocking new physics, revealing a universe where even the very nature of reality can change under the right circumstances. Q-stars unveiling the unknown realm of hybrid stellar objects. Neutron stars push the boundaries of what we understand about matter under extreme conditions, but there may be objects that are even more exotic. Q-stars are hypothetical celestial bodies that exist in a strange state between neutron stars and black holes. Unlike ordinary neutron stars, Q-stars could contain an entirely new form of matter. A neutron star is formed post-supernova of a massive star, leaving behind a dense core. If the core is massive enough, gravity crushes it into a black hole. But in some cases, instead of collapsing into a singularity, the core may reach an in-between state, forming a Q-star. These objects are thought to be made of something other than neutrons and quarks. One idea is that Q-stars contain a special kind of vacuum energy that resists gravitational collapse, allowing them to remain stable despite their extreme density. This would make them different from any known object in the universe. Unlike black holes, Q stars would not have an event horizon. Matter and radiation could escape from their surfaces, meaning they would still interact with the universe around them. However, their densities would be high enough to make them nearly indistinguishable from black holes in some observations. They might be only slightly larger than the event horizon of a black hole of the same mass, meaning they could mimic the way black holes bend and distort light. This could explain some astronomical objects that appear to behave like black holes, but do not show all of the expected characteristics. One possibility is that they contain a type of exotic matter held together by forces beyond the standard model of particle physics. Some scientists have suggested that Q stars could be made of a hypothetical substance known as Bose-Einstein condensates. In this state, particles behave as a single entity, flowing without friction and forming structures that defy normal expectations. If Q stars are made of such a material, they could represent a completely new phase of matter, existing only under the most extreme conditions in the universe. Another possibility is that Q stars are the remnants of stars that have gone through an unusual type of collapse. In normal stellar evolution, a star burns its fuel until it can no longer support itself against gravity. The most massive stars collapse into black holes, while less massive ones form neutron stars. But if a star's core reaches a critical density and temperature, it might form a Q star instead of following the usual path. Their existence would suggest that there are still undiscovered phases of matter waiting to be found. Some theories propose that Q stars could slowly transform into black holes over time, collapsing as their internal structure changes. This would mean that some black holes we observe today might have once been Q stars, making them part of an evolutionary process rather than a final state. Detecting Q stars is a challenge because they resemble black holes in many ways. Both are incredibly compact and have strong gravitational fields that bend light. However, Q stars might produce unusual radiation signatures due to their unique internal structure. Some astronomers have suggested looking for stars that emit bursts of energy without showing the telltale signs of a neutron star's magnetic field. Others have proposed searching for compact objects that seem too small to be neutron stars, but do not show the complete darkness expected from a black hole. If Q stars are made of exotic particles that interact weakly with normal matter, they could provide a new way to study dark matter. Some scientists have even suggested that small Q stars might be drifting through space undetected, contributing to the hidden mass of galaxies. Observatories designed to study gravitational waves, such as LIGO and Virgo, could potentially detect signals from the collisions of these strange objects. If two Q stars were to merge, they would produce ripples in spacetime similar to those seen in neutron star collisions, but with subtle differences that could reveal their unique nature. Magnetars unleashed, magnetic fields that defy imagination. Magnetars are rare neutron stars that possess magnetic fields so intense that they can tear apart matter at the atomic level. With magnetic forces trillions of times stronger than those on Earth, magnetars generate bursts of energy that can be detected across vast cosmic distances. While a typical neutron star already has a powerful magnetic field, a magnetar's is on an entirely different scale. If Earth had a magnetar strength field, it would erase credit cards from orbit and distort the chemistry of human brains. The magnetic fields of these stars are so strong that they can alter the behavior of atoms, turning ordinary matter into a strange, stretched form of existence. Any object coming too close would be torn apart before it even reached the surface. The origins of these extreme magnetic fields remain uncertain. One leading theory suggests that magnetars form when a collapsing star spins rapidly at birth, winding up its magnetic field in a process similar to how a dynamo generates electricity. This rapid spinning, combined with the density of a neutron star amplifies the magnetic field to its unimaginable intensity. Another idea is that some magnetars might form from mergers of smaller stellar remnants, producing an even greater magnetic force in the process. Magnetars are prone to violent outbursts of energy known as starquakes. These events occur when the immense magnetic field distorts the crust of the neutron star, causing it to crack and release sudden bursts of gamma rays and X-rays. These explosions are some of the most energetic events in the universe, capable of outshining entire galaxies for brief moments. In 2004, one such event from a magnetar over 50,000 light-years away briefly affected Earth's atmosphere, demonstrating the staggering reach of these cosmic powerhouses. The energy released in these flares can be millions of times more powerful than anything produced by the Sun. In a fraction of a second, a magnetar can unleash more energy than our Sun emits in an entire year. This makes them key candidates for some of the most powerful cosmic flashes ever recorded, including fast radio bursts. While not all fast radio bursts are linked to magnetars, some have been traced back to them, suggesting that their explosive nature may be responsible for some of the most enigmatic signals in deep space. One of the strangest effects of a magnetar's intense magnetic field is its ability to warp empty space. In quantum physics, the vacuum of space is not truly empty, but instead teeming with virtual particles that pop in and out of existence. Under normal conditions, these effects are too small to notice. But near a magnetar, the field is so strong that it distorts the vacuum itself, creating a phenomenon known as vacuum birefringence. This effect causes light to behave in strange ways, altering its polarization as it passes through the star's magnetic influence. Observing this process in action could provide a rare glimpse into the nature of quantum physics on a cosmic scale. Unlike regular neutron stars, which remain relatively stable, magnetars appear to be short-lived in cosmic terms. Their intense magnetic fields gradually decay, releasing energy over thousands of years. As this happens, the star's activity slows down, and it eventually becomes a more typical neutron star. This suggests that magnetars represent a brief but incredibly powerful stage in the life cycle of certain stars, existing only for a short time before fading into obscurity. Some researchers believe that the strongest gamma-ray bursts, which are among the most powerful explosions in the cosmos, may be triggered by newly formed magnetars. If a magnetar is born in the aftermath of a supernova, its rapid rotation and intense magnetic field could drive an enormous explosion, blasting matter outward at nearly the speed of light. These bursts could influence the formation of stars and even seed the cosmos with heavy elements. Quantum foam, the chaotic underbelly of space-time. The idea of quantum foam was first introduced by physicist John Archibald Wheeler in the 1950s. He theorized that if one could zoom in far enough, space would resemble a turbulent, foamy structure where tiny distortions ripple in and out of existence. The reason for this strange behavior lies in the principles of quantum mechanics, which allow for unpredictable fluctuations, where energy and matter briefly appear and disappear, creating a churning, frothy texture to space itself. This foamy nature of space arises because of the Heisenberg uncertainty principle. At microscopic levels, energy and matter cannot be precisely defined at any given moment. Instead, tiny fluctuations in energy constantly occur, creating brief, fleeting distortions in space-time. These fluctuations happen at scales so small, around the Planck length, that they are currently impossible to detect with any known technology. These minuscule distortions might even create temporary wormholes that flicker in and out of existence. These wormholes would be far too small and unstable for anything to travel through, but their existence would suggest that space-time is far more complex than it appears on the surface. Physicists know that space is not truly empty. It is filled with vacuum energy, a hidden force that fluctuates constantly. The presence of quantum foam could help explain how this vacuum energy behaves and why we do not see its effects in everyday life. Some scientists even believe that these fluctuations might be connected to dark energy. Even though it operates at scales far beyond our current technological reach, scientists have proposed several ways to detect its influence. One idea is that tiny distortions in the path of light, travelling across vast distances, could reveal the presence of quantum foam. If quantum foam exists, then light passing through the universe might be subtly scattered by these random fluctuations, leaving behind a faint but detectable signature. Some researchers have attempted to test this idea by examining the light from distant quasars. If quantum foam exists, then the light from these distant objects should become slightly blurred or scattered as it travels through space. So far, no definitive evidence has been found, but ongoing experiments continue to search for any subtle hints of this hidden structure. If quantum foam is real, it might mean that spacetime is an emergent property arising from the chaotic interactions of these microscopic fluctuations. If true, this would challenge some of the most basic assumptions about reality and force physicists to rethink the nature of space, time, and existence itself. Some physicists believe that quantum foam could also play a role in the search for a unified theory of physics, a single framework that explains both quantum mechanics and general relativity. One of the biggest challenges in modern physics is that these two theories, while both incredibly successful, seem to contradict each other when applied to extreme conditions, such as the interiors of black holes or the moment of the Big Bang. Quantum foam could provide a missing link between them, offering insights into how gravity and quantum mechanics might be reconciled. If space-time is foamy and constantly fluctuating, then time, at the smaller scales, could be fragmented, disjointed, and subject to random fluctuations. This would mean that our perception of time as a steady, continuous stream is merely an illusion that emerges at larger scales, where quantum effects average out. The seemingly solid and predictable world we experience may be built upon an unpredictable, fluctuating foundation. This would mean that even the most fundamental concepts in physics, such as distance, motion, and causality, might be emergent properties rather than absolute truths. Vacuum instabilities and false vacuum decay, the universe's hidden countdown. The concept of vacuum stability comes from quantum field theory, which describes the behavior of energy fields that fill all of space. These fields determine the properties of fundamental particles, such as electrons and quarks, and influence the way forces like electromagnetism and gravity operate. The vacuum of space is defined by the lowest energy state that these fields can occupy. However, the crucial question is whether the vacuum we currently exist in is the lowest possible state, or merely a temporary one. A false vacuum is a state that appears stable but is not truly at the lowest possible energy level. It is like a ball resting on the side of a hill rather than at the bottom of a valley. The ball may sit there for an incredibly long time, appearing motionless, but if given the right push, it will roll down to a lower, more stable position. If our universe exists in a false vacuum rather than a true vacuum, then it is possible that a shift to a lower energy state could happen at any moment. This process is known as false vacuum decay, and its consequences would be nothing short of catastrophic. If a lower energy state does exist, then the transition could be triggered by a quantum fluctuation, a tiny, random disturbance at the smaller scales. Once triggered, the shift would spread outward in a sphere, expanding at the speed of light. Within this expanding bubble, the laws of physics could be completely different. The fundamental constants that govern the universe, such as the charge of the electron or the strength of gravity, might change, rendering everything inside unrecognizable. Atoms, molecules, and even the very structure of space-time could be torn apart or reshaped into something entirely new. What makes this scenario particularly unsettling is that if such a transition were to begin, We would never see it coming. Because the bubble of the new vacuum would expand at the speed of light, there would be no warning, no sign of impending doom. One moment, everything would be as it is now, and the next, the entire observable universe could be altered beyond comprehension. The possibility of vacuum decay is not just a theoretical curiosity. Some interpretations of modern physics suggest that it is a real and unavoidable outcome, particularly when considering the properties of the Higgs boson. This particle, discovered in 2012, plays a crucial role in determining the masses of fundamental particles. Precise measurements of the Higgs boson suggest that the vacuum of our universe may indeed be metastable, meaning it is not in the lowest energy state, but instead perched in a delicate balance that could one day tip. While the idea of vacuum instability paints a dramatic picture of cosmic destruction, it is important to consider the timescales involved. Even if the universe is in a false vacuum, the transition could take an incomprehensibly long time to occur, longer than the current age of the universe by trillions or even quadrillions of years. Some calculations suggest that natural processes, such as black hole formation and quantum fluctuations, could trigger vacuum decay. But the likelihood of this happening any time soon is extremely low. Some have speculated that powerful particle accelerators, such as the LHC, could create conditions that destabilize the vacuum. However, most physicists dismiss this concern, noting that far more energetic processes occur naturally in the universe, such as cosmic ray collisions, without causing vacuum decay. If the vacuum of space were truly on the brink of collapse, then it likely would have happened long ago due to these natural events. Some theories propose that vacuum transitions could be responsible for the birth of new universes. In this view, what we perceive as a catastrophic event, the decay of a false vacuum, might actually be the process through which new cosmic regions are formed. In this way, the end of one universe could mark the beginning of another, with different physical laws and constants. Some cosmologists speculate that the early universe may have undergone multiple phase transitions, shifting from one vacuum state to another as it evolved. These transitions may have played a role in shaping the structure of the cosmos, determining the distribution of galaxies, and setting the stage for the physical laws we observe today. What does it mean to exist in a cosmos that is fundamentally unstable? If the laws of physics themselves can change, does that imply that reality has no ultimate foundation? These are questions that go beyond physics, touching on the nature of existence itself. Symmetry, breaking in extreme conditions, the birth of cosmic complexity. The universe appears structured and complex, filled with galaxies, stars, and planets. But in its earliest moments, it was anything but. It was a dense, hot expanse of energy and particles in near-perfect uniformity. At that time, the fundamental forces of nature may have been indistinguishable from one another, and matter itself may not have existed in any familiar form. Yet something happened that disrupted this perfect balance. Tiny differences emerged, creating a break in symmetry that led to the vast and intricate cosmos we see today. Symmetry is a fundamental concept in physics. It refers to situations where certain properties remain unchanged even when transformations occur. In the early universe, before forces and particles separated, there may have been a high degree of symmetry, so much so that everything was evenly distributed. But as the universe expanded and cooled, that symmetry could no longer hold. Some parts of the universe shifted in slightly different ways than others. Certain forces and particles took on distinct roles, while others became irrelevant. This process, known as symmetry breaking, allowed for the birth of cosmic complexity. One of the most significant instances of symmetry breaking likely occurred when the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, split from a single unified force. Scientists suspect that in the earliest fractions of a second after the Big Bang, these forces were not separate at all. they were part of a higher-order symmetry, a kind of cosmic uniformity where all interactions behaved the same way. But as the universe cooled, each force acquired its own distinct properties. Gravity remained the force responsible for large-scale attraction, while the other three dictated interactions between particles. This separation was a key moment in cosmic history, allowing matter and energy to behave in ways that would ultimately lead to the formation of everything we observe today. The effects of symmetry breaking were not limited to the forces of nature. The structure of matter itself was influenced by this process. In the early universe, matter and antimatter existed in equal amounts, at least in theory. Antimatter is a counterpart to normal matter, with the same mass but opposite electrical charge. If the universe had remained perfectly symmetrical, matter and antimatter should have annihilated each other completely, leaving behind nothing but energy. But something disrupted that balance. A tiny asymmetry allowed for a small surplus of matter to survive, while most of the antimatter was wiped out. This imbalance, possibly only one extra particle of matter for every billion particles of antimatter, was enough to seed the formation of all the stars, planets, and galaxies that fill the cosmos. Another key example of symmetry breaking occurred during cosmic inflation. This period of rapid expansion stretched the fabric of space at an incredible rate, smoothing out large-scale irregularities, but also amplifying tiny quantum fluctuations. These fluctuations, minuscule differences in density, were imprinted onto the universe, forming the blueprints for future galaxies. The result was that some regions of space contained slightly more matter than others, setting the stage for gravitational collapse and the birth of large-scale cosmic structures. Without these early imbalances, the universe might have remained an even, lifeless sea of particles, rather than the complex and varied cosmos it became. Inside stars, nuclear fusion depends on delicate balances of pressure and temperature. Small deviations in these conditions can determine whether a star ends its life as a white dwarf, a neutron star, or a black hole. Similarly, planetary systems form through gradual accretion, where slight variations in the distribution of dust and gas lead to the emergence of planets with vastly different compositions and orbits. These are all echoes of the fundamental asymmetries that began in the early universe. Some theories suggest that hidden symmetries still exist in nature but are masked by the conditions of our present cosmos. If these symmetries were restored, perhaps under extreme conditions in high-energy particle collisions or in the cores of massive stars, entirely new physical behaviours could emerge. Some scientists even speculate that additional forces or unknown particles could be revealed if symmetry breaking could be reversed or manipulated. There is also the possibility that further symmetry breaking events could occur in the future. If the universe is still evolving, then it is not necessarily locked into its current form. A future shift could trigger another transition, fundamentally changing the nature of reality. Whether this would lead to new physical laws or a complete restructuring of the cosmos is unknown. Entanglement in extremis. Quantum connections under intense gravity. Quantum entanglement is one of the strangest phenomena in physics. It suggests that two or more particles can become so deeply connected that their states are instantly linked, no matter how far apart they are. A change in one particle seems to affect the other instantly, even across vast distances. This bizarre connection has been tested and confirmed in experiments. Normally, entanglement is studied in controlled laboratory settings, where scientists observe how photons, electrons, or even atoms behave when they are paired in this way. But what happens when entangled particles are placed in some of the most extreme environments in the universe, near black holes, neutron stars, or in the warped fabric of spacetime itself? Gravity is a force that bends and shapes spacetime. The stronger the gravitational field, the more space and time are distorted. Near the event horizon of a black hole, gravity becomes so strong that nothing can escape. If quantum entanglement still operates under such conditions, it raises profound questions about how information and physical laws behave in these extreme settings. In normal circumstances, entanglement persists across great distances. But the event horizon represents a kind of boundary in spacetime, where information may be lost forever. Does the connection between the two particles break? If not, does this mean that some information is still being transmitted across the event horizon, despite classical physics saying that nothing can escape? Some theories propose that entanglement could provide a hidden link between the interior and exterior of black holes. One idea, known as the ER equals to EPR conjecture, suggests that entangled particles might be connected by microscopic wormholes. Wormholes, also known as Einstein-Rosen bridges, would act as tunnels through spacetime, allowing information to remain linked even when one particle crosses the event horizon. If this idea holds true, it would mean that black holes do not destroy information entirely, but instead encode it in different ways. Another consequence of extreme gravity is time dilation. If one particle of an entangled pair is near a black hole, while the other is far away, their experience of time would be drastically different. The particle closer to the black hole would experience time at a much slower rate, meaning any attempt to measure their entangled states could be affected by the time distortion. Some researchers suggest that this could lead to new insights into how quantum mechanics and gravity interact. Exotic pair production. Transmutations in the void. At the heart of pair production is the idea that energy and matter are interchangeable. Einstein's famous equation, E equals mc squared, expresses this principle, showing that mass and energy are just different forms of the same thing. Normally, we think of energy being stored in matter, like the fuel in a rocket, or the food we eat. But in extreme conditions, the process can work in reverse. Pure energy can give rise to particles that have mass. For this transformation to happen, certain conditions must be met. The energy involved has to be high enough to create a particle and its antiparticle at the same time. This is because all fundamental particles have counterparts with opposite properties. Electrons have positrons, protons have antiprotons, and even more exotic particles have their own antimatter twins. When enough energy is focused into a single point, such as in high-energy collisions or near extreme gravitational fields, the fabric of reality itself responds by producing matter and antimatter from the void. One of the best-known places where pair production happens is near black holes in the form of Hawking radiation. But pair production is not limited to black holes. In the early universe, when temperatures were unimaginably high, energy was so concentrated that particle-antiparticle pairs were forming everywhere. This was a time of rapid creation and destruction, where matter and antimatter were locked in a struggle for survival. For reasons not yet fully understood, a tiny imbalance favoured matter, allowing it to dominate the universe we see today. High-energy cosmic rays, which constantly bombard Earth from space, also create bursts of pair production when they collide with atoms in our atmosphere. These collisions generate showers of particles, some of which briefly exist before transforming into more stable forms. Particle accelerators like the LHC recreate similar conditions. In these collisions, scientists have observed the spontaneous creation of matter-antimatter pairs, providing direct proof of how energy can transform into particles under the right conditions. One of the most puzzling aspects of pair production is what happens to the antimatter that is created. In most cases, antimatter quickly encounters its matching particle and annihilates in a flash of energy. But in the vastness of space, it is possible that some antimatter particles avoid immediate destruction, drifting for long periods before eventually colliding with normal matter. There is even speculation that entire regions of the universe might be dominated by antimatter, separated from ordinary matter by unknown cosmic forces. Could pair production be harnessed as a source of energy? Could it help explain the missing pieces of our understanding of the universe? If the balance between matter and antimatter had been only slightly different in the past, would an entirely different cosmos have emerged? Temporal anomalies and time crystals. New paradigms of cosmic rhythm. One of the most intriguing breakthroughs in modern physics is the discovery of time crystals. Unlike ordinary crystals, which form repeating structures in space, time crystals display a form of repetition in time itself. This means that instead of remaining static, like a diamond or a snowflake, a time crystal undergoes periodic changes in its physical state without any external force acting on it. It cycles through different configurations at regular intervals, as though caught in a perpetual rhythm, yet without expending energy. The idea of time crystals emerged from a branch of physics known as condensed matter theory. In 2012, Nobel Prize-winning physicist Frank Wilczek proposed the concept, suggesting that certain systems could exhibit motion without external input, a property that seemed impossible under classical physics. Normally, perpetual motion is ruled out by the laws of thermodynamics. Any system that continues to move indefinitely should eventually lose energy to friction or other dissipative effects. But time crystals do not behave like normal objects. Instead, they exist in a state of broken time symmetry, meaning they do not experience time the way ordinary matter does. Real-world time crystals were first observed in 2016, when researchers found that certain quantum systems could indeed exhibit repeating motion without external energy. These crystals were made from tiny, carefully arranged particles, like trapped ions or specially designed magnetic materials that responded to internal quantum interactions in a way that forced them into rhythmic cycles. Unlike a ticking clock that requires winding or a planet that moves because of gravity, these systems oscillated naturally, seemingly detached from external forces. One of the strangest aspects of time crystals is that they remain stable despite their movement. Ordinarily, when a system changes over time, it eventually settles into a lower energy state. A spinning top, for example, slows down and stops due to friction. But time crystals avoid this fate because they do not transfer energy in the usual way. Their repeating patterns exist in a kind of quantum loophole, where the normal rules of thermodynamics do not fully apply. Time crystals have potential implications for a wide range of scientific fields. In quantum computing, for example, they could help maintain stable quantum states for longer periods, making calculations more reliable. Since they resist conventional decay, time crystals might also be used in ultra-precise timekeeping devices, surpassing even the best atomic clocks available today. Beyond time crystals, other temporal anomalies challenge traditional views of time's flow. In the presence of intense gravitational fields, for instance, time slows down, a fact confirmed by experiments with atomic clocks flown on spacecraft. But theoretical models hint that under even stranger circumstances, time might loop, fracture, or take on patterns as unusual as those found in space-time itself. One of the most speculative but fascinating ideas is that time may not be a smooth, continuous flow, but rather a sequence of discrete moments, similar to the way digital screens display images using individual pixels. Some theories suggest that on the smaller scales, time might behave like a series of flashes, updating reality in increments too tiny to detect with current technology. This idea is somewhat analogous to how time crystals exhibit structured repetition, except on an even deeper, more fundamental level. Time could become knotted in certain conditions. Just as tangled magnetic fields in the sun can twist and snap, releasing vast amounts of energy, some physicists propose that time may experience similar distortions in high-energy environments, such as those near black holes or in the early moments of the universe. If true, this could mean that time has a more intricate structure, potentially allowing for effects like closed time loops or regions where different rates of time exist side by side. Some exotic theories even suggest that time could be multidimensional, much like space. While humans experience time as a linear progression from past to future, mathematical models allow for additional directions in time, just as there are multiple dimensions in space. If time had more than one dimension, events could unfold in ways that are currently inconceivable, with certain processes branching or curving in ways that do not follow a strict cause and effect sequence. The study of time anomalies also intersects with research into dark energy and cosmic expansion. Could time be stretching along with space? Could there be hidden structures in the way time flows, just as galaxies form complex patterns across the cosmos? These questions point to a deeper mystery about the nature of time. Is it an inherent property of the universe or merely a construct of human perception? Many of the laws of physics function just as well when time is mathematically reversed. This means that, at least in theory, time does not necessarily have a preferred direction. Yet in reality, we experience a clear forward motion, where the past is fixed and the future remains unknown. The reason for this arrow of time is still an open question, with some physicists suggesting that entropy, the tendency for disorder to increase, drives time's apparent direction. Rethinking ultramassive black holes. At the heart of almost every large galaxy in the universe sits an ultramassive black hole. These monsters are millions or even billions of times the mass of our Sun. Unlike the smaller black holes formed from collapsing stars, these giants exist on an entirely different scale, anchoring the galaxies that revolve around them. They dictate the movement of stars, shape cosmic evolution, and influence the fate of entire regions of space. Yet despite their colossal presence, they remain some of the least understood objects in the universe. These black holes are so massive that their gravitational pull extends for light years. The one at the centre of the Milky Way, known as Sagittarius A star, is relatively small compared to others, containing about 4 million times the mass of the Sun. In larger galaxies, however, black holes can reach extraordinary sizes. The behemoth at the centre of Messier 87 weighs in at around 6.5 billion solar masses. Even that is dwarfed by TON 618, an ultramassive black hole estimated to have over 66 billion times the mass of the Sun. These objects are so heavy that they distort not just the space around them, but the structure of their entire galaxies. These ultramassive black holes are engines of destruction and creation, pulling in gas, stars, and even other black holes. Around them, matter spirals inward, forming a glowing disk of superheated material. The energy released as this material falls toward the event horizon can be astonishing, sometimes outshining entire galaxies. The most extreme cases produce quasars, some of the brightest and most energetic objects in the universe. A quasar powered by a feeding ultramassive black hole can radiate more energy than trillions of stars combined, sending powerful jets of charged particles shooting across space at nearly the speed of light. Black holes emit no light of their own, revealing their presence only through their effects on surrounding matter. Observing them requires detecting the glow of their accretion disks, measuring the movements of nearby stars, or capturing the faint signals of radio waves emitted by their swirling magnetic fields. It was only recently, in 2019, that scientists produced the first direct image of a black hole's event horizon using a global network of telescopes to capture the glowing ring around the monster in Messier 87. Unlike smaller black holes, which form from dying stars, ultramassive black holes seem to have existed early in the universe's history, already vast in size. How did they grow so large so quickly? One possibility is that they formed from the collapse of the first massive stars, merging rapidly with others in a chain reaction of growth. Another idea suggests they may have emerged directly from enormous clouds of gas, collapsing into black holes without first forming stars. Some theories even propose that these monsters could be relics from the earliest moments of the universe, structures that formed before normal matter had fully settled. The energy they release can be so powerful that it prevents further star formation, blowing away the very gas needed to create new stars. In some galaxies, this feedback effect acts like a cosmic thermostat, regulating the rate of star birth and preventing runaway growth. In others, black holes trigger the formation of new stars by compressing clouds of gas with their outflows. Some of the largest galaxies in the universe may owe their structures to the presence of these massive gravitational anchors. Some galaxies are home to more than one, evidence of past collisions and mergers. When galaxies collide, their central black holes spiral toward each other, slowly drawing closer until they eventually merge into an even larger singularity. These events send ripples through space-time itself, producing gravitational waves that can be detected across the universe. The merger of ultra-massive black holes is one of the most violent and extreme processes known, releasing more energy in an instant than all the stars in a galaxy combined. As astronomers look deeper into the cosmos, they continue to find evidence of black holes more massive than previously thought possible. Some have suggested that there could be black holes exceeding 100 billion solar masses, pushing the limits of what we understand about gravity and cosmic structure. Cosmic strings and filaments, the delicate threads of universal structure. Cosmic strings are hypothetical, one-dimensional defects in space-time, remnants from the early universe that could still stretch across the cosmos today. Unlike ordinary filaments made of matter, cosmic strings would be defects in the very fabric of the universe itself, formed in the high-energy conditions moments after the Big Bang. These structures, if they exist, would be unimaginably thin, thinner than a proton, yet incredibly dense, with a single string stretching across the universe containing more mass than an entire galaxy. Just as imperfections can form when water freezes into ice, physicists believe that phase transitions in the early universe may have created defects in space-time. Cosmic strings would be one type of these defects, long, unbroken lines where the universe's fundamental fields remained in a different state than the surrounding space. Unlike cracks in ice, though, these structures would not break apart or disappear. Instead, they would persist over billions of years, stretching and moving through the cosmos. If cosmic strings exist, they would create extreme effects on their surroundings. Because of their immense density, they would warp space-time around them, acting like gravitational lenses capable of bending light from distant objects. If a cosmic string were to pass between Earth and a faraway galaxy, it could create a strange optical effect, splitting the galaxy's image into two identical copies. These lensing effects could be one of the few observable clues that cosmic strings are out there, hiding within the vastness of space. As they move through the universe, they can form loops, oscillating and shedding energy in the form of ripples in space-time. Unlike gravitational waves from colliding black holes, which come in short bursts, cosmic string waves could produce continuous signals, faint but stretching across the universe. While cosmic strings remain theoretical, there is another kind of cosmic thread that we can observe, the vast filaments of the cosmic web. Unlike cosmic strings, these filaments are made of ordinary and dark matter, forming a massive intergalactic network. Simulations of the early universe suggest that small variations in density caused by quantum fluctuations shortly after the Big Bang gradually grew under the influence of gravity. Over billions of years, matter clumped together along these invisible strands, forming the scaffolding upon which galaxies were built. The scale of these filaments is staggering. Some stretch hundreds of millions of light years, forming connections between galaxy clusters that span the universe. In between these threads lie immense voids, vast empty regions where few galaxies exist. The contrast between these dense, thread-like structures and the surrounding emptiness reveals the universe's true shape, a web-like network far larger than any single galaxy or cluster. One of the largest known structures in the cosmic web is the Sloan Great Wall, a filament of galaxies more than 1 billion light-years long. This immense structure is not a solid object, but rather a dense region where galaxy clusters are connected by smaller bridges of dark matter and gas. Other large-scale structures, such as the Hercules Corona Borealis Great Wall, hint that the universe's largest features may be even more extensive than previously thought. Despite their vast size, these filaments are fragile in the grand scheme of cosmic time. Over billions of years, as the universe expands, they will stretch and weaken. The dark matter within them, which holds galaxies together, will continue to influence their structure. But the filaments themselves may eventually fade as gravity loses its grip against the accelerating expansion of the universe. The relationship between cosmic strings and the cosmic web remains speculative, but some theories suggest that if cosmic strings exist, they could have influenced the formation of these massive filaments. As defects in space-time, cosmic strings would have provided pathways along which matter could gather, creating early structures that later became the foundation for galaxies. While no direct evidence supports this idea, it raises an intriguing possibility that the largest structures in the universe may have been shaped by some of the smallest and most fundamental processes in physics: particle cascades and anomalous showers, unveiling the universe's hidden fireworks. High-energy events generate cascades of particles, producing showers that ripple through space and even reach Earth's atmosphere. While invisible to the human eye, they reveal some of the most extreme processes in the cosmos, showing how matter behaves under conditions impossible to recreate in laboratories. These particle cascades originate from the most energetic cosmic phenomena: supernova, gamma-ray bursts, and the violent interactions of cosmic rays with interstellar matter. When a highly energetic particle collides with another, it sets off a chain reaction. The initial impact shatters the particle into smaller fragments, which themselves collide with others, producing an expanding shower of secondary particles. This cascade effect continues until the energy is dispersed into lower energy forms, often resulting in bursts of radiation, neutrinos, or even antimatter. Some of the most dramatic cascades come from cosmic rays, high-energy particles travelling through space at nearly the speed of light. These particles, mostly protons and atomic nuclei, originate from supernova remnants, active galactic nuclei, and other powerful astrophysical sources. When a cosmic ray strikes Earth's atmosphere, it collides with air molecules, triggering an extensive air shower. The resulting explosion of subatomic particles spreads downward, creating a fleeting but intense cascade that instruments on the ground can detect. Scientists use vast detector arrays to capture these events. Observatories such as the Pierre Auger Observatory in Argentina and the telescope array in Utah spread thousands of sensors across wide areas to record the telltale flashes of particle showers. When a high-energy cosmic ray enters the atmosphere, it creates a burst of secondary particles that move faster than the speed of light in air, producing a faint blue glow known as Cherenkov radiation. These flashes allow scientists to track the energy, direction, and possible origin of the incoming cosmic ray. Not all cascades behave as expected. Some of the most puzzling detections involve anomalous showers, particle interactions that do not conform to standard physics. In rare cases, detectors have recorded showers that appear to come from cosmic rays with energy levels far beyond what any known astrophysical source should be capable of producing. These ultra-high energy cosmic rays, sometimes called "oh my God" particles, carry energy millions of times greater than the most powerful human-made particle accelerators. So far, their origin remains a mystery. Another anomaly comes from particle showers that seem to move in the wrong direction. Normally, cosmic rays enter Earth's atmosphere from space, producing cascades that move downward. However, instruments like the Antarctic Impulsive Transient Antenna, or ANITA, have detected unusual particle showers appearing to emerge from the ground or ice, as if they were moving upward. These events defy explanation, as they suggest the presence of unknown particles capable of travelling through the planet in ways that current physics cannot fully account for. Some scientists speculate that these could be signals of exotic particles, possibly linked to new physics beyond the standard model. Even within expected particle cascades, there are surprises. Some high-energy events produce antimatter. While antimatter is rare in the universe, certain cosmic interactions generate positrons, or even antiprotons. These unexpected antimatter signatures raise questions about whether some cosmic sources might naturally produce more antimatter than previously thought, possibly hinting at unknown physics at play. Neutrinos, nearly massless particles that barely interact with matter, also emerge from particle showers. Unlike other cascade products that are quickly absorbed by their surroundings, neutrinos pass through planets, stars, and galaxies largely undisturbed. They carry valuable information about the conditions in which they were formed, acting as cosmic messengers from the most extreme environments. Facilities like IceCube in Antarctica monitor vast volumes of ice for the faint traces of neutrinos from deep space, hoping to link them to specific cosmic events such as black hole jets or neutron star collisions. Particle cascades are crucial for understanding how cosmic radiation affects planetary environments. On Earth, the atmosphere shields the surface from the full force of these energetic showers, but in space, astronauts and spacecraft are exposed to higher levels of radiation from cosmic events. Understanding these interactions helps in planning future space missions and developing protective technologies for long-duration human spaceflight. Even planets and moons in our solar system experience their own versions of these cascades. Mars, with its thin atmosphere, sees more cosmic radiation reach its surface, and instruments aboard rovers like Curiosity have recorded how these high-energy interactions influence Martian conditions. In more distant worlds, gas giants like Jupiter and Saturn have strong magnetic fields that capture and redirect charged particles, creating dynamic radiation belts and particle showers that shape their magnetospheres. Beyond our solar system, particle cascades may play a role in shaping the evolution of galaxies. High-energy cosmic rays contribute to ionization processes in interstellar space, affecting the formation of new stars and the chemistry of planetary systems. Some theories suggest that bursts of cosmic rays from nearby supernovae could even influence climate patterns on Earth by affecting atmospheric ionization and cloud formation. Future space-based observatories, such as those planned for deep space cosmic ray detection, may provide new insights into the most extreme sources of high-energy particles. These observations could help uncover the origins of the most energetic events in the universe. Micro-black hole collisions, cataclysms on the smaller scales. Unlike their supermassive counterparts that anchor galaxies, micro-black holes would be far smaller, potentially no bigger than an atom or even smaller. They might form under extreme conditions, such as during the violent early moments of the universe when matter was packed into an unimaginably small space. Some theories suggest that high-energy cosmic events, like the collision of ultra-energetic particles, could briefly create micro-black holes, though these would evaporate almost instantly due to Hawking radiation. If micro-black holes were to collide, the event would be an extraordinary dance of intense gravitational forces. When two large black holes merge, they create powerful gravitational waves that ripple through spacetime. On a smaller scale, micro-black hole collisions would produce similar but much weaker disturbances. However, because these objects exist in a regime where both quantum mechanics and gravity are equally important, Their interactions could reveal new insights into how the universe operates at the most fundamental level. If two micro-black holes were to collide and merge, the way their masses and event horizons interact could provide clues about the quantum structure of spacetime itself. Some theoretical models propose that micro-black holes might not just merge, but could also recoil or even transform into other exotic objects. Because these black holes would be extremely small, quantum effects would likely dominate their behaviour, meaning they wouldn't necessarily act like scaled-down versions of large black holes. They could create temporary, unstable fluctuations in spacetime, producing a brief but intense gravitational interaction before evaporating in a burst of radiation. Understanding these effects could offer hints about the true nature of black hole interiors. They exist. They might be incredibly rare, or they may form and vanish too quickly for current instruments to detect. If micro-black holes are naturally occurring, they could potentially be scattered throughout the universe, forming in extreme environments such as the dense cores of neutron stars or within the intense energy fields surrounding black hole event horizons. In such cases, occasional interactions between these small black holes could lead to rapid bursts of radiation or gravitational anomalies that might be detectable with future space-based telescopes. If humanity ever reaches the point where we can artificially create and control micro-black holes, such interactions could be studied in a controlled setting. This would provide direct insights into the nature of spacetime, black hole evaporation, and the link between quantum mechanics and gravity. But such an experiment remains far beyond our current technology. While traditional black hole studies focus on massive objects in space, micro-black holes and their potential collisions introduce elements of quantum uncertainty, wave-particle duality, and even ideas about extra dimensions. Some speculative theories suggest that if extra dimensions exist, micro-black holes might be more common than expected, forming as a result of interactions within those hidden layers of reality. Matter-antimatter imbalances, the persistent cosmic conundrum. For there to be an excess of matter today, something must have tipped the scales in its favour. Scientists believe this imbalance arose during the earliest moments of the universe, within the first fractions of a second after the Big Bang. One possible explanation comes from a concept known as charge parity, or CP, violation. In physics, symmetry plays a crucial role, and one of the key principles is that the laws of nature should treat matter and antimatter almost identically. However, in certain rare interactions, this symmetry is broken, meaning matter and antimatter behave slightly differently. Experiments with subatomic particles called mesons have provided evidence of CP violation, showing that nature does, under specific circumstances, favour matter over antimatter. But the effect observed so far is tiny, far too weak to explain the overwhelming dominance of matter in the universe. If CP violation is responsible, it must be happening at a much greater scale than currently understood. Another possible explanation involves a process called leptogenesis, which focuses on neutrinos. Some theories suggest that in the early universe, extremely heavy versions of neutrinos decayed in a way that produced more matter than antimatter. These decays could have introduced an asymmetry before most particles had even fully formed, setting the stage for the imbalance that followed. The strong nuclear force, which binds protons and neutrons together inside atomic nuclei, might also have played a role. Some models suggest that under extreme conditions, the interactions of quarks, the fundamental building blocks of protons and neutrons, could have created a matter surplus. If certain reactions slightly favoured quarks over antiquarks, even by an almost immeasurable amount, that small difference could have amplified as the universe expanded and cooled. Scientists continue searching for evidence of matter-antimatter asymmetry in experiments on Earth and observations of the distant universe. Astronomers search for traces of antimatter in space. If significant regions of antimatter existed somewhere in the cosmos, we might expect to see signs of matter-antimatter annihilation at the boundaries where they meet. So far, no such signals have been detected. Some researchers have even proposed the possibility that antimatter exists in a separate, hidden sector of the universe. If antimatter regions formed early on and became isolated from matter-dominated regions, they might still exist, but be located beyond our observable universe. However, this idea has little evidence currently. Understanding the matter-antimatter imbalance has profound implications for physics as a whole. It suggests that our current theories of particle interactions are incomplete. If new physics is at play, discovering what caused this asymmetry could lead to breakthroughs in our understanding of fundamental forces. It could also provide clues about why the universe took the particular shape it did, forming galaxies, stars, and planets, instead of dissolving into pure energy. If we ever find a complete explanation for why matter triumphed over antimatter, it could also have practical implications. Antimatter, when harnessed, is an incredibly powerful energy source. If the fundamental mechanisms behind its scarcity were better understood, it might lead to new ways of generating or capturing antimatter in controlled environments. Dark stars, illuminated by dark matter annihilation. Though it cannot be seen, dark matter appears to make up most of the universe's mass, shaping galaxies and bending the light of distant objects with its gravitational pull. While its exact nature remains unknown, some theories suggest that dark matter consists of particles that can collide and annihilate each other, releasing energy in the process. If such particles were concentrated enough in certain regions of the early universe, they might have powered entire stars. These dark stars would have formed in a different way than the ones we see today. A typical star begins its life when a cloud of gas collapses under its own gravity, growing hotter and denser until nuclear fusion ignites in its core. But in the early universe, before many of the heavier elements existed, dark matter may have collected within collapsing gas clouds, preventing them from forming traditional stars. Instead of relying on fusion, these early structures may have drawn their heat from the constant annihilation of dark matter particles trapped inside them. Unlike modern stars, a dark star would have glowed in a more diffuse and extended way. The heat from dark matter annihilation would have spread throughout the star, keeping it cool enough to grow much larger than ordinary stars. Some models suggest that dark stars could have reached sizes hundreds or even thousands of times larger than the Sun, their vast, faintly glowing forms drifting through the primordial universe. In a normal star, nuclear reactions consume hydrogen, eventually leading to the star's death. But a dark star, fed by the steady process of dark matter annihilation, might have been able to last for millions or even billions of years, glowing softly while traditional stars were still in their infancy. These long-lived dark stars might have played a crucial role in shaping the early universe, providing light and energy in an era before the first galaxies fully formed. Could any still be out there? If a dark star were to run out of dark matter fuel, it might collapse into a more familiar type of star, eventually burning through nuclear fusion like any other. But in some cases, if enough dark matter remained, these stars might have continued their unusual existence deep into cosmic history. The James Webb Space Telescope and other advanced observatories are now detecting galaxies from a time when the first stars were just beginning to form. If dark stars existed, their unusual properties might create unexpected signatures in the light coming from these distant epochs. Because dark stars would have been much larger and more diffuse than regular stars, their spectra might look different from what scientists expect from normal early universe objects. If a dark star eventually gathered enough mass, it might have collapsed directly into a black hole without ever going through a supernova explosion. If this happened often enough, it could provide a new explanation for the existence of supermassive black holes. If they are found, they could change our understanding of how the first sources of light in the universe came to be, offering a new perspective on the balance between visible matter and the dark. Naked singularities, unmasked points of infinite curvature. For decades, physicists have operated under the belief that singularities must always remain hidden behind an event horizon. This idea is known as the cosmic censorship hypothesis, proposed by physicist Roger Penrose in 1969. The hypothesis suggests that nature has a way of preventing singularities from being observed, ensuring that the most extreme distortions of spacetime remain locked away inside black holes. The reasoning behind this idea is that naked singularities could cause serious problems for our understanding of physics. Without the protective barrier of an event horizon, a singularity could theoretically influence the surrounding universe in unpredictable ways. The very fabric of reality near such an object might behave in ways that defy our understanding of cause and effect. Despite the cosmic censorship hypothesis, theoretical studies suggest that naked singularities could form under certain conditions. Some models of black hole formation indicate that if a collapsing mass sheds enough angular momentum or charge, the event horizon might never fully form, leaving the singularity exposed. Rapidly rotating black holes, for example, could potentially reach a state where their event horizons disappear entirely. If such objects exist, they could provide a direct window into the most extreme effects of gravity. The equations of general relativity do not explicitly forbid naked singularities. In fact, certain solutions to these equations naturally allow for their existence. The Kerr solution, which describes rotating black holes, suggests that if a black hole spins fast enough, it could prevent an event horizon from forming at all. Another example comes from the Reissner-Nordström solution, which describes charged black holes. If a black hole carries more charge than mass, the event horizon vanishes, leaving a singularity completely exposed. While such conditions may be highly unlikely in nature, they are not impossible. One of the biggest concerns is that naked singularities could break the known rules of cause and effect. In normal circumstances, an event horizon acts as a one-way boundary, ensuring that anything crossing it is forever removed from the rest of the universe. This prevents information from escaping a singularity, maintaining the order of spacetime. But in the case of a naked singularity, there would be no such boundary. Information and radiation could, in principle, emerge from the singularity and influence the rest of the cosmos. The laws of physics might become unpredictable near such an object, allowing signals to travel in ways that seem to violate the normal flow of time. The extreme conditions near a naked singularity could reveal hidden aspects of spacetime that are otherwise concealed behind event horizons. Studying the behavior of matter and radiation near such objects could offer clues about the deeper structure of reality, potentially bridging the gap between gravity and quantum physics. No direct evidence of naked singularities has been found. However, some astrophysical observations hint at their potential existence. Certain high-energy cosmic events have led some scientists to speculate that they might be powered by processes involving naked singularities. Additionally, some gravitational wave signals detected from colliding black holes exhibit properties that are difficult to explain using traditional models, leading to speculation that they could involve objects with exposed singularities. Attempts to rule out naked singularities entirely have been met with challenges. While many solutions in general relativity suggest that event horizons will always form around collapsing masses, some simulations indicate that under the right conditions, a collapsing star could bypass this stage and form a singularity without a horizon. These cases often involve highly specific scenarios, such as extreme rotation or rapid mass shedding, but they cannot be dismissed outright. Some theories propose that even if a naked singularity were to form, quantum effects might step in to resolve the problem. Spacetime fluctuations could prevent the formation of a true singularity, instead replacing it with a more stable quantum structure. This might mean that what appears to be a naked singularity at first glance could actually be something entirely different, perhaps a gateway to a new phase of matter. Since black holes are detected through their gravitational influence on nearby objects, identifying a singularity without an event horizon requires indirect methods. Some researchers have suggested that if naked singularities exist, they might produce unique observational signatures, such as unusual lensing effects or radiation patterns. The Event Horizon Telescope, which famously captured the first image of a black hole's event horizon, might one day provide insights into whether such extreme objects exist. If they do exist, they could provide an unparalleled opportunity to study the most extreme forces in the cosmos, offering a glimpse into the raw, unfiltered heart of gravitational collapse. If they do not, their absence could reinforce the idea that nature has built-in safeguards that prevent such extreme violations of physics. Exotic boson stars, unusual, luminous entities of dark matter. Stars shine because of nuclear fusion. Deep within their cores, hydrogen atoms are pressed together under immense gravity, forming helium and releasing energy in the process. But the cosmos may harbour stars that do not rely on nuclear fusion, yet still manage to exist as luminous, stable structures. These are called boson stars, theoretical entities made up of exotic particles that behave in ways completely different from the familiar atoms of conventional stars. Unlike the stars that populate the night sky, boson stars are not composed of protons, neutrons, or electrons. Instead, they are thought to be made primarily of bosons, a distinct category of fundamental particles that includes force-carrying particles like photons and gluons. More interestingly, some theories suggest that dark matter could be composed of undiscovered bosonic particles. If true, then boson stars might exist as strange, glowing entities formed largely from dark matter. What makes bosons different from other types of particles is their ability to occupy the same quantum state. Ordinary matter, made up of fermions like electrons and protons, follows a rule that prevents identical particles from existing in the same place at the same time. This is what gives regular stars their structure, layers of atoms pressing against each other, creating pressure and supporting the star's shape. But bosons do not follow this rule. They can overlap and merge into a single quantum state. A boson star would be an enormous macroscopic quantum object. Instead of being supported by the usual balance between gravity and nuclear fusion, it would be held together by the delicate interplay of gravitational forces and the strange properties of bosons. Some models suggest that these stars could form through the gradual accumulation of bosonic dark matter, which might clump together under gravity, condensing into a stable, self-contained structure. Traditional stars shine because their hot plasma emits radiation, producing light and heat. But boson stars may not emit light in the same way. Depending on the properties of their constituent particles, they might be nearly invisible, glowing only faintly at specific wavelengths. Some versions of boson stars could radiate in the radio or infrared spectrum rather than visible light, making them difficult to detect with conventional telescopes. Other models predict that boson stars could shine more brightly, particularly if their particles interact with normal matter in unusual ways. Some theories suggest that if a boson star were composed of charged bosons, it could generate electromagnetic radiation, making it detectable. In such a case, its light might not resemble that of an ordinary star, but could instead exhibit peculiar variations in brightness or unusual spectral signatures. The interaction between bosonic dark matter and surrounding plasma could create flickering or pulsating effects, making these stars appear different from anything seen before. In standard stars, fusion generates outward pressure that counteracts gravity, preventing collapse. But boson stars would be stabilized by quantum effects, specifically the way bosons behave when they form a collective state. If too much matter accumulates in a boson star, it might reach a critical mass where quantum effects are no longer sufficient to counteract gravity, potentially leading to collapse into a black hole. Some black holes could have once been boson stars that grew beyond their stability limit. If a boson star were to pass close to a black hole, it might behave in unexpected ways. Unlike ordinary matter, which would be stretched and torn apart by tidal forces, boson stars could exhibit wave-like behaviours, rippling and distorting as they interact with the extreme gravitational environment. Because they do not have a solid surface like traditional stars, they might bend and distort light passing near them in ways that resemble black hole lensing effects. However, unlike black holes, boson stars would not have an event horizon. This means that a careful analysis of their gravitational influence might reveal telltale differences between boson stars and true black holes. Certain compact objects detected in space have mass ranges that do not fit neatly into the categories of known black holes or neutron stars. Some of these objects could be boson stars, hidden in plain sight, masquerading as familiar celestial bodies. Detecting a boson star would be challenging, but not impossible. Researchers are looking for indirect signs of their existence, such as deviations in the expected movements of nearby stars. Some ongoing and future observational projects might provide the necessary tools to confirm or rule out the existence of these exotic objects. Theoretical work on boson stars continues to explore their possible properties and behaviours. Some studies suggest that they could exist in various states, including rotating configurations that create swirling, vortex-like patterns in spacetime. Others propose that boson stars might act as cosmic ghosts, passing through galaxies without interacting strongly with normal matter, making them even harder to detect. Some researchers even speculate that boson stars could form binary systems, orbiting one another in a delicate quantum dance that could leave detectable signatures in gravitational wave data. Gravastars, cosmic alternatives to black holes. A gravastar, or gravitational vacuum star, is based on the idea that what we think of as a black hole might not be a true singularity at all. Instead, the collapse of a star could create a structure where extreme conditions prevent the formation of a singularity. Instead of a point of infinite density, a gravastar would have an interior made of an exotic form of space known as a gravitational vacuum. This would be surrounded by an ultra-thin shell of normal matter, forming an object that behaves like a black hole in many ways, but with crucial differences. From the outside, it could appear almost identical to a black hole. If someone were observing a gravastar from a distance, they might see the same gravitational lensing effects, the same ability to bend light, and the same extreme warping of space. However, the key difference is what happens inside. Unlike black holes, which contain an inescapable singularity, gravastars would have an interior made up of a strange repulsive force that resists further collapse. This would prevent the complete breakdown of space and time, keeping the laws of physics intact. A gravastar could provide a way for information to be preserved, perhaps stored in the exotic matter making up its structure. When a massive star collapses, it typically forms either a neutron star or a black hole, depending on its mass. For a gravastar to form, an additional mechanism must come into play, something that prevents the star's core from becoming infinitely dense. The proposed solution involves an exotic substance with negative pressure, similar to what is thought to drive the accelerated expansion of the universe. This repulsive force present within the gravastar's core would counteract gravity and stabilize the structure, creating an object that outwardly behaves like a black hole, but has no true event horizon. Because they lack a singularity and an event horizon, they might not produce the same effects as a traditional black hole when interacting with nearby matter. If a black hole and a gravastar were placed side by side, both would attract surrounding gas and dust, with intense gravitational pull. However, near the surface of a gravastar, particles might behave differently. Instead of falling in irreversibly, matter might accumulate in a thin shell, heating up and radiating energy in a pattern distinct from the high-energy emissions typically seen around black holes. Certain compact objects detected in space exhibit behaviours that deviate slightly from what black hole theory predicts. These deviations could be caused by alternative structures like gravastars, though more research is needed to confirm or refute this possibility. When two black holes merge, they produce a signature gravitational wave pattern that scientists can detect. If two gravastars were to merge instead, their waveforms might differ slightly due to their unique internal structure. Some researchers are exploring whether existing gravitational wave detections contain subtle hints of such differences, which could provide indirect evidence for gravastars. Black holes slowly evaporate through Hawking radiation. If gravastars exist, they might undergo a different kind of decay or transformation. Some theories suggest that over immense timescales, a gravastar could slowly leak energy in a way that prevents it from ever fully collapsing. Others propose that if the repulsive force maintaining a gravastar were to weaken, the structure could eventually give way and turn into a true black hole. Primordial black holes, relics from the universe's dawn. Unlike black holes formed from dying stars, primordial black holes would have originated from intense density fluctuations in the early universe. The Big Bang did not create a perfectly uniform cosmos. Instead, tiny variations in density arose as space expanded. In some regions, the concentration of matter may have been so extreme that gravity instantly overwhelmed all other forces, crushing the matter into black holes almost immediately after the universe began. The size of these primordial black holes would depend on the scale of the density fluctuations that created them. Some could be tiny, no larger than an atom, while others might be thousands of times the mass of the Sun. If primordial black holes formed at extremely small sizes, they would have completely disappeared by now. However, those above a certain mass would still be around today, hidden among the galaxies, drifting through interstellar space, or even clustered together in ways we have yet to detect. Some scientists have proposed that dark matter might not be a new type of particle, but rather a vast collection of primordial black holes. If these ancient objects are common enough, their combined gravitational influence could explain many of the effects attributed to dark matter. It is possible that primordial black holes played a role in the formation of supermassive black holes. Observations show that some supermassive black holes existed surprisingly early in cosmic history, long before galaxies had enough time to grow large enough to form them through normal processes. One explanation is that primordial black holes, already present from the beginning, acted as seeds for these massive objects, gradually consuming matter and merging with each other until they became the enormous black holes we see today. Hyperdense quark stars, beyond neutron star limits. Quarks are the smallest known components of matter, forming protons and neutrons inside atomic nuclei. Under normal conditions, quarks are never found alone. They are always bound together in groups of 2 or 3, held tightly by the strong nuclear force. But in the extreme environment of a collapsing neutron star, the pressure may become so immense that even these bonds are torn apart, allowing quarks to move freely. This transformation would mark the birth of a quark star. If quark stars exist, they would be among the densest objects in the universe, second only to black holes. While neutron stars are already mind-bogglingly compact, squeezing over a solar mass into a sphere just 20 kilometers across, quark stars could be even smaller and denser. The transition from neutron matter to quark matter could shrink a star's radius, while making it even more gravitationally intense. The exact size of such an object depends on the properties of quark matter, which remain largely unknown. But some models suggest that quark stars could be only a few kilometers wide. Theoretical models suggest that there is a point at which no further collapse is possible without forming a black hole. Neutron stars represent one limit, where neutrons resist further compression through quantum mechanical forces. But if quark matter is stable, it could define a new, even more extreme limit before an object finally succumbs to gravity's pull and vanishes behind an event horizon. Detecting a quark star would be incredibly difficult, as they might appear similar to neutron stars from a distance. Both would be compact, rapidly spinning, and emitting intense radiation from their surfaces. However, there could be subtle clues. For example, the way a quark star vibrates in response to disturbances, such as a nearby object's gravitational pull, might be different from that of a neutron star. Observing these oscillations through precise measurements of pulsars could offer hints that some stars are even denser than expected. Another possible signature comes from the cooling behavior of these stars. Neutron stars cool gradually as they lose heat over millions of years. However, if quark matter is present, it could cool much more rapidly due to different interactions between particles inside the star. This rapid cooling could cause some neutron stars to become unexpectedly dim, hinting that their interiors have undergone a phase transition. If a neutron star collapses into a quark star, or if quark matter undergoes unexpected transitions, it could release a brief but powerful burst of energy visible across vast cosmic distances. On Earth, recreating the conditions needed to break protons and neutrons into free quarks requires the use of particle accelerators. Even then, the quark-gluon plasma produced in these experiments exists only for a fraction of a second before cooling back into normal matter. A quark star would be a natural laboratory for studying matter at densities far beyond anything achievable in an Earth-bound experiment. There are some candidates that astrophysicists suspect could be more than just neutron stars. Observations of compact stars that seem too small or too massive to be explained by current neutron star models have led to speculation that these could be quark stars. One such example is the object known as XTEJ 1739-285, which appears to be more compact than a neutron star should be, leading some to wonder if it might contain quark matter. The transition from a neutron star to a quark star would not be a gentle process. If quark matter is stable at extreme densities, a neutron star reaching a certain critical mass could suddenly collapse into a smaller, denser state, releasing a tremendous amount of energy. This process could produce a burst of radiation, possibly explaining some of the unusual high-energy events observed in the cosmos. If the conditions inside them allow for even greater compression, they could eventually collapse further, forming a black hole. In this case, quark stars could be a brief, intermediate stage in the life cycle of some collapsing stars. Alternatively, if quark matter is stable over long timescales, these objects could persist for billions of years, acting as strange, dim remnants of massive stars. WIMP stars, theoretical constructs of weakly interacting massive particles. One of the leading candidates for dark matter is a theoretical class of particles known as WIMPs, weakly interacting massive particles. While they remain hypothetical, WIMPs have inspired an intriguing idea: the possibility of WIMP stars, celestial objects made predominantly of these enigmatic particles rather than ordinary matter. If WIMPs exist, they would be expected to interact with each other only rarely. But when they do, they might annihilate in tiny bursts of energy. This annihilation could provide a steady heat source, allowing a WIMP star to maintain its structure without the need for nuclear fusion. Instead of being powered by the collision of hydrogen atoms, as our Sun is, these stars would be sustained by the rare but powerful interactions between dark matter particles. The first generation of stars in the universe, known as population 3 stars, formed from pure hydrogen and helium, marking the transition from a dark, formless cosmos to one filled with radiant light. But if enough dark matter had accumulated in certain regions, it is possible that WIMP stars could have formed instead of, or alongside, these first conventional stars. Since their energy source depends only on the slow interactions of dark matter particles, rather than the limited supply of hydrogen and helium, they could persist for billions or even trillions of years. Because dark matter does not interact with light in the same way as ordinary matter, these stars might be nearly invisible, detectable only by the subtle glow produced by their dark matter annihilation. They might not have a defined surface like a traditional star, instead appearing as diffuse, ghostly halos of radiation rather than as solid objects. Some theories suggest they could be much larger than conventional stars, with their energy spread out across vast regions of space rather than concentrated in a dense core. One of the biggest challenges in detecting dark matter is that it does not readily interact with ordinary matter or light, making it nearly impossible to observe directly. But if WIMP stars formed in the early universe and still exist today, their unique energy signatures could offer a rare glimpse into the fundamental properties of these elusive particles. Some theories suggest that they may have existed only in the early universe, forming in dark matter-rich regions before normal stars took over as the dominant source of light. If this is the case, they may no longer exist in detectable numbers, having either collapsed or transformed into other cosmic structures over time. However, if dark matter remains dense enough in certain regions, it is possible that WIMP stars could still exist today, hidden within galactic halos or isolated in the depths of intergalactic space. Some scientists have suggested that they could be responsible for excess gamma-ray emissions observed in the centre of the Milky Way, which some believe may be the signature of dark matter annihilation. Quantum nucleation points, seeds of unconventional cosmos. Quantum fluctuations occur because, at the most fundamental level, empty space is filled with an ever-shifting background of virtual particles. While most of these fluctuations cancel out or disappear before they can have any lasting impact, some may become stable under the right conditions. When this happens, a quantum nucleation point could form, a localized disturbance that grows rather than fades. If such an event occurs in a high-energy environment, it could trigger the emergence of an entirely new structure, one that could range from an exotic particle to an astrophysical object of unprecedented form. One possibility is that quantum nucleation points could serve as the birthplaces of strange matter. If a stable nugget of strange matter were created through quantum nucleation, it could, in theory, grow by consuming nearby atomic nuclei, converting normal matter into a denser, more exotic state. If such nucleation points formed in the hearts of neutron stars, they could trigger the conversion of entire stellar remnants into strange stars. Unlike normal stars, which shine through fusion, or neutron stars, which are sustained by neutron degeneracy pressure, strange stars could exist in an entirely different regime of physics, stabilized by the fundamental properties of quark interactions. In some versions of cosmology, our universe may be just one of many, part of a vast multiverse where new cosmic domains continuously emerge. If quantum fluctuations in space can generate self-sustaining regions of energy density, they might create localized patches that break off and expand into separate universes. This concept, often explored in inflationary cosmology, suggests that within the vast quantum foam of reality, nucleation points may serve as the triggers for entire cosmic bubbles, each one potentially governed by different physical laws. A nucleation point could trigger the formation of a true vacuum bubble, expanding outward at the speed of light and fundamentally altering the very fabric of reality. While no direct evidence of large-scale nucleation events has been observed, experiments continue to push the limits of what is possible, searching for signs that such processes might play a role in cosmic evolution. Speculative lepton stars, stellar entities dominated by electron degeneracy. Electrons, belong to a category of particles called leptons, which, unlike protons and neutrons, do not experience the strong nuclear force. Instead, they are governed by the weak nuclear force and electromagnetism. More importantly, they obey the Pauli exclusion principle, a fundamental rule in quantum mechanics that states no two identical fermions, like electrons, can occupy the same quantum state within a confined space. In dense environments, this principle generates what is known as degeneracy pressure, a force that prevents electrons from being squeezed into an arbitrarily small volume. White dwarfs, the remnants of low to medium mass stars, already rely on electron degeneracy pressure for stability. Once fusion ceases, the core of a white dwarf is held up entirely by the quantum mechanical resistance of electrons against further compression. However, white dwarfs still originate from normal stars, formed through a long evolutionary process involving nuclear fusion. A lepton star, in contrast, would be different from the very beginning, never relying on fusion at all, but instead maintaining its structure purely through the properties of its electrons. For a lepton star to exist, an extreme mechanism would have to create an environment where electrons vastly outnumber protons and neutrons. This could occur in the high-energy conditions of the early universe, where certain processes might have led to a region dominated by leptons. Alternatively, they might form in a highly magnetized stellar remnant, where interactions between strong magnetic fields and quantum effects create an electron-rich environment. Unlike white dwarfs, which contain a mix of atomic nuclei and electrons, a lepton star would have little to no nuclear material. This would make it an incredibly strange object. The density of such a star would be immense, but not quite at the level of neutron stars. The gravitational forces attempting to collapse the star inward would be countered only by electron degeneracy pressure, creating an equilibrium not seen in conventional stellar models. In some extensions of particle physics, additional leptons beyond electrons, muons, and tau particles might exist. If these new leptonic particles were stable, they could accumulate in sufficient quantities to form an entirely new type of stellar object. In this case, the star's structure would be determined not just by electrons, but by an interplay of multiple lepton species, each obeying quantum mechanical restrictions that prevent them from collapsing into a singularity. Lepton stars would likely have some truly bizarre properties. Their light emissions would differ greatly from traditional stars. Instead, their temperatures would be dictated by the energy states of the electrons themselves. This could make them appear dimmer than conventional stars, possibly emitting only in specific bands of the electromagnetic spectrum. Their long-term evolution would also be unlike that of any known stellar object. Without fusion to provide an outward flow of energy, a lepton star might cool over immense timescales, gradually radiating away its energy until it became a dark, cold relic. If a lepton star were to gain additional mass, it could approach a critical threshold where even electron degeneracy pressure would no longer be sufficient to prevent collapse. At this point, the star could undergo a transformation into a quark star, where quark matter takes over as the dominant force against gravity. If lepton stars were to be discovered, they could revolutionize our understanding of stellar physics. They would demonstrate that objects can exist outside the normal pathways of star formation, opening up new possibilities for how matter organizes itself under extreme conditions. It would also raise profound questions about the universe's composition. If lepton-dominated structures can form, what other exotic configurations of matter might exist, waiting to be uncovered? Cosmic solitons, self-sustaining waves in the fabric of reality. Solitons are a rare and unusual kind of wave. Unlike ordinary waves, they do not spread out or lose their form over time. Instead, they maintain a stable shape as they move through space, acting almost as if they are solid objects. While solitons have been observed in water, plasmas, and even fiber optics, some physicists speculate that similar structures could exist on a much grander scale, moving through the universe as persistent, self-sustaining waves in the fabric of reality itself. In ordinary wave behaviour, energy disperses. A wave travelling through water, for example, will eventually fade as friction and interference break it apart. But a soliton behaves differently. It is a special kind of wave where energy is confined in such a way that it resists dispersion. Instead of spreading out, it stays intact, travelling for vast distances while keeping its shape. In the right conditions, solitons can even interact with one another, briefly merging before continuing on their way, unaffected. Some models suggest they might appear as waves in dark matter or dark energy, subtly influencing the structure of galaxies. Others propose that solitons could be disturbances in the quantum vacuum, creating pockets of high energy that travel through space like invisible pulses. In these scenarios, solitons could act as hidden architects of cosmic structures, shaping the universe in ways not yet understood. In the moments following the Big Bang, the cosmos was filled with fluctuating energy fields. If solitonic waves formed during this period, they may have survived to the present day, influencing the way matter and energy distribute themselves across vast cosmic scales. Some researchers speculate that certain unexplained patterns in the CMB could be remnants of ancient solitonic waves still moving through space. Solitons could also be connected to cosmic strings. Like solitons, cosmic strings are stable and persistent, stretching across galaxies without losing their structure. If solitons and cosmic strings are related, they could form a hidden framework that subtly shapes the universe, guiding the formation of galaxies and galaxy clusters. In the dense plasma surrounding neutron stars or black holes, powerful magnetic fields and intense gravitational forces could create conditions where solitonic waves emerge. These waves might travel through space, carrying information about their origins and providing clues about the physics at work in some of the universe's most extreme regions. Some models even suggest that solitons could exist at a quantum level, moving through the vacuum of space as coherent energy packets. Some galaxies exhibit strange, wave-like ripples in their outer regions, which could be signs of passing solitonic waves. Similarly, unexplained fluctuations in gravitational lensing might be evidence of solitons subtly altering space-time. If such waves exist, they could provide a new way to explore the invisible forces shaping the universe. One of the most speculative yet fascinating ideas is that solitons could act as carriers of information on a cosmic scale. Some theories suggest that these waves could encode quantum states, preserving information as they move across vast distances. If true, solitons could serve as a natural medium for transferring data through space, potentially playing a role in unknown physical processes that extend beyond our current understanding. If a solitonic wave were to encounter the event horizon of a black hole, would it be absorbed, or would it persist in some altered form? Some models propose that solitons might orbit black holes, caught in stable configurations that could eventually release bursts of energy. If they exist, they could also be studied in controlled laboratory conditions, where scientists might learn to harness them for practical purposes. In fields such as quantum computing and high-energy physics, understanding solitonic behaviour could open new possibilities for manipulating energy and information at fundamental levels. Fuzzball paradigm, a string theory approach to black hole interiors. In classical physics, black holes are thought to contain a singularity. This idea has puzzled scientists for decades because it suggests that space and time cease to function in any meaningful way. But string theory, a framework that attempts to unify gravity with quantum mechanics, offers an alternative picture. Instead of a singularity, it proposes that black holes might be something else entirely, a tangled mass of fundamental strings known as a fuzzball. The fuzzball paradigm suggests that black holes do not have an empty event horizon, with a mysterious singularity hidden inside. Instead, the entire structure of the black hole is made up of highly compressed strings, the fundamental building blocks of the universe in string theory. These strings form a dense, complex object that has volume and avoids the issue of infinite density. In this view, a black hole is not a hole in space, but a massive, tangled object with no empty interior. The fuzzball theory offers a potential solution to the black hole information paradox by suggesting that the infalling matter becomes part of the tangled string structure, preserving information in some form. One of the key differences between a fuzzball and a traditional black hole is what happens at the event horizon. In the standard model, the event horizon is a smooth boundary with no structure or physical properties. But in the fuzzball model, the event horizon is a chaotic surface made of energetic strings. Instead of falling into a void, matter interacts with this surface, potentially radiating back out rather than disappearing forever. This could provide a mechanism for black hole evaporation that aligns with Hawking radiation. In the classical model, Hawking radiation is generated just outside the event horizon. In the fuzzball paradigm, the radiation emerges directly from the surface of the tangled strings, carrying away energy in a way that might allow for the retention of information. Another implication of the fuzzball concept is that it challenges the need for a singularity at all. In the fuzzball model, string interactions prevent the collapse from reaching an infinite state. Instead, the fundamental strings spread out, forming an extended object with a complex internal structure. This means that the interior of a black hole could be a tangled, fluctuating region, rather than a simple point of destruction. In standard general relativity, the size of a black hole is determined by the Schwarzschild radius, the distance at which light can no longer escape. But in the fuzzball picture, the horizon might be fuzzy and fluctuate depending on the internal string structure. This could have implications for how black holes grow, shrink, and merge with each other in extreme cosmic environments. One of the challenges in studying the fuzzball model is that string theory operates at scales far smaller than anything we can currently observe. String interactions take place at the Planck length. Because of this, most evidence for the fuzzball idea comes from mathematical models rather than direct observations. If black holes are fuzzballs rather than empty voids, their mergers might create subtle differences in the wave patterns. Some researchers are looking for signs of echoes in gravitational wave signals, which could indicate that the event horizon of a black hole is not a smooth boundary, but a complex string-based surface. Some simulations suggest that matter falling onto a fuzzball would interact with its surface to produce unusual high-energy emissions. If future telescopes detect unexpected signals from black hole accretion disks, it could hint at a more complex structure than currently believed. If black holes are not singularities but extended objects, it could mean that the Big Bang itself might not have originated from an infinitely dense point. Instead, the universe's beginning might involve a more complex string-based structure. This could open the door to new theories about cosmic origins. Despite its potential advantages, the fuzzball paradigm is not without challenges. It is deeply rooted in string theory, a framework that has yet to be fully proven. While string theory provides a mathematically elegant way of describing fundamental forces, it has yet to make predictions that can be tested in experiments. Some physicists remain skeptical of the fuzzball idea, arguing that simpler solutions might exist for the information paradox and black hole structure. However, as more observational data becomes available, especially from gravitational wave detectors and high-energy astrophysical observations, researchers may find ways to probe the true nature of black holes. Whether black holes turn out to be fuzzballs or something else entirely, the search for answers continues to push the boundaries of what we know about the universe. And on that exciting note, this journey comes to an end. What would you like for us to talk about next? Comment below, and if you enjoyed the video, consider leaving a like and subscribing to the channel. Thanks for watching.